just a few months, this is going to be the fastest Subaru drag racing shifter in the world. Now, if you're familiar with Dark Matter X, then you know we do not mess around when it comes to shifter engineering. We are currently a few weeks into the design, and today we start the prototyping. Alright, I'm really excited. I just got a bunch of different bearings in the mail to test with our prototype. I called up our supplier, Enduro Bearings, and Jonathan hooked it up on some different sizes and some different specs of bearings that sounded like they would fit and be applicable for our design requirements here. So let's open this up and check them out. So we ordered up 5 different styles of bearings, and we've got 3 of each. So when we design this thing out, we can build a few different prototypes of each one. If I end up deciding there's a couple that I want to use, or maybe just move forward with one of them, I'll have lots of options here to sort of determine that with. This here is a EnduroMax radial bearing that would actually fit onto the shaft we're using if we machine the shaft down and create a shoulder. This has a black oxide coating on it to give it some better corrosion resistance. And let's open up the seal here and show you what it looks like. This bearing is even smaller than this bearing here. So for this one, if we decide we want to have a smaller kind of like circumference on this race here, we would also have a smaller shaft diameter here, and we could machine our shaft here down to have a shoulder for our bearing to go right on it. So here's another option. This is going to be the same style as this bearing, just doesn't have the black oxide coating, and it's a little bit smaller. This bearing here is not like these bearings. It's actually more of a traditional radial bearing where it has a cage in here, or it should have a cage when we pull the seal off. So these are EnduroMax bearings. There's no cage, and they have way more ball bearings in them than this one. But there's a lot more rolling resistance on those bearings when compared to a caged bearing. So here's an option for us. This diameter here actually fits right over our shaft, or it should. We'll kind of figure that out later, how that's going to attach on there. There could be a little interference on here, but this is very closely matched to this shaft diameter, so there wouldn't be any like machining down or having to create like a large shoulder on our shaft as if we were using the smaller bearing. There you have it. You can see that cage in there, holding and separating all of the ball bearings apart, keeping them that nice controlled distance there. Way smoother, way easier to move than the EnduroMax ball bearings with no cage. Here we have a much larger caged radial bearing as compared to this one right here. You can see that size difference. So right here, this is going to give us just more distance from the shaft to the outer race, and it's a larger bearing, so this bearing can take a higher load. It's got more support in it. It rolls nice and smooth. I mean, wow, that's crazy. I'm like barely touching that, and it's just like such a smooth, nice rolling bearing. This might be the winner right here, guys, but we still have another set we got to go over. So yeah, let's pop the seal off of this one and see how much larger it looks inside compared to its little baby brother here. Wow, look at that. That is night and day. That difference there. That cage is beefy. This inner race is beefy. The bearings are beefy. Everything about this bearing is bigger, but that doesn't necessarily mean that it's going to be better for our application. So this bearing here is also a caged radial bearing like these. It's just a smaller version. So should probably put it right in the middle there. And let's go ahead and take a look at what this looks like. There you have it. You have a much smaller version than this bearing here. And it's still got the cage in there. You can see the cage. You can see the ball bearings in there. And you never know. This bearing could have advantages in this application over this bearing, right? We don't know. We got to test some stuff. We got to start designing this. And we got to see there could be geometric differences in this design where we need to utilize a smaller bearing versus a bigger bearing. So we ordered a whole bunch of stuff here to test and try out, start prototyping with. So which bearing do you think is going to be the one that ends up winning here? I have a feeling that it's probably, if I had to guess, it's probably either going to be this bearing here that we end up using or this guy here. I think it's going to be one of these, but you never know. We're just going to have to test it, try it out. So there's 3 main points that I want to identify that I'm going to use to help determine like which bearing is going to be working better than the others for this design. So the first thing is just going to be the resistance of the bearing. So what I mean by that is you have your outer race and your inner race, and there's a force that it takes to move that outer race relative to the inner race. And it's easier to do on the caged bearings compared to the Enduro Max bearings, which have no cage. There's much higher resistance it takes to break that force. And I know we're talking about a minuscule amount, but it is going to come into play with this design. So we want to be thinking about when we're choosing which bearings to go with, the actual resistance in the bearing itself. And the second thing would be the inner race. So on the bearings, we have this inner race here on every single one of them. It's this steel band that is in the very middle, and that steel band is the same size on these 3 bearings for the inside. And then on these bearings, they are a different size. So this one, you can tell, is much smaller. This one's a little bit larger. And this is the shaft that we're actually going to be using. This isn't the exact one. This is just the size, the correct size of the shaft that we're going to be using in this design. So these inner races are matched to that size. These inner races are not. So we may need to do some machining down of that shaft and create a shoulder so that they fit. If we decide these are the bearings that we want to go with, there's always give and take. So some of the take is going to be that we have to machine that down, and that could lower the actual shear strength and create a higher point stress on our shaft. So it might not end up mattering as far as the strength goes, but that's something to consider here, is machining that down. Is that worth it? Is that necessary to use these bearings compared to these ones over here, where we could keep that same consistent cross-sectional material amount all the way through with these bearings. And the last thing would be the outer race to inner race distance. So between the outer race and the inner race, you can see there's a distance here that is much larger on this bearing here between the outside of the outer race and the inside of the inner race. Now that distance is different on every single one of these bearings. Now when we go to design this thing, when the bearing moves down one of its like stages of stops, and then it moves along a guide, there's going to be a distance there that we have to work with that's different on each and every one of these bearings. Now, when there's a force applied to the bottom or the side of that bearing, it's going to be applied into this shaft. So when that force is applied into the side here, let's just say the bearing's that large, this way and possibly down the shaft too, there's going to be a difference in force on this shaft and on the whole system, the larger we go out in diameter. So the further we move out, that force is going to become greater and greater on this shaft because of the torque. Because of the torque it's going to be applying on this shaft. So the larger we go out with that force, the more it's going to be applied into that shaft. So it may end up being that we want to use a bearing with a smaller distance here so we can get that force to be applied directly closer to this shafting where the bearing's being supported. And you may not think like it's that important, but we're trying to design this thing properly and make sure nothing is being like stressed or loaded too much. And we want to have like a very safe design here. Something that is just going to be very repeatable, very predictable every time it's used. We want to consider these things as far as choosing which bearing to be using in this design. So I've mocked up the bearing here on a shaft just to kind of visualize what we're going to be doing here. I 3D printed this sort of support bracket here, and I inserted a bushing for that shafting in there. And this is kind of what I'm looking at and working with before I start like fully designing and speccing out and drafting up all the parts for this. And I noticed something that's going to come into play here that I wanted to go over. It's going to be really, really important for this design to work, especially over time. We want this design, this lockout, to work thousands of times over and over and over and just be repeatable and trustworthy. We don't want to kind of design things on the edge here and be kind of unsure, because this is somebody's entire build. This is their car. This is their passion, their life has gone into these cars. So we need to make sure this thing is just over the top. Like there's no corners cut. Like this thing is taking all of my brain power and my skill. So I just want to get back on track here and show you something. So this shaft is currently only supported up here, and I want to add a guide down here. So something that's going to happen, I have my little force gauge here. I want to show you something that's going to happen is when this bearing is loaded on the side to guide the shifter from second gear diagonally into third gear, there's going to be like quite a lot of force potentially in the driver's hand being applied into the shifter and then translated down into the bearing and ultimately into the guide to push it over. So something I was thinking about was, is it really smart to only support this shaft that is going to be moving up and down on this spring system just at one point? So if we apply a little bit of a force here, you can see what's going to happen is I'm just going to move this up a little bit. Okay. And then we have this spring pressure up here. So this spring is going to be responsible for pushing. You can see it's trying to push the shifter down. But you see how it's not smooth? I'm going to show you why. In our current design over on the shifter there, we have a shaft here. And in reality, this shaft is, none of this is going to be proportion. I'm just trying to show you what exactly is happening kind of like on a fundamental level of why there's resistance and how to free that up and make it operate smoother. So here's our shaft, and then on the outside of the shaft we have our bushing. So let's say the bushing is right here. So what's happening is when a force is being applied below that bushing on one edge of the shaft, this bushing is actually camming in here. It's twisting. It's not supported down here. There's nothing stopping it except this right here. This is the edge, and it's really a circle. So this is a side view. If we looked from the top down, it would look just like this. It would look like that. Shaft, bushing. So what's happening is you're contacting here, and you're also contacting here. It's twisting. We're having this sort of twisting happening when it's loaded in the side. So then when our spring is trying to return our shaft down through our bushing when we want it to, it is going to be pressing and forcing up against this edge, right? Because we're going to be shifting so quick, the stuff's going to be getting loaded and unloaded. We want that spring to just be ready to push this shaft straight down and not have to wait for this shaft to straighten out. Because if it's twisting, then we have this twisted and this shaft has to reorient straight in the bushing. We don't need to wait for that. We can actually just create a design here where it's always going to be right in line with the spring force. And the way we're going to do that is we're actually going to put another bushing down here. Boom, boom. Let me just clean that up real quick. Okay, so we're going to put another bushing down here. And then our shaft is going to go all the way down here through this other bushing. Right, so we've got that. We've got our second bushing down here, and our force is still going to be applied here. Our bearing is still going to be here. We're not changing the position. And what's going to happen now is instead of having this twisting of the shaft when it's loaded, because we're going to have now a reaction happening here, keeping this nice and straight, what's going to happen is this isn't going to get twisted anymore. This whole entire shaft is going to get loaded to these sides of the bushings. So in here and in here, the whole thing's going to get loaded to the side, boom, by the bearing. And then when that spring applies that force down, it's just going to, boom, snap straight down. That's my theory. We'll go ahead and actually like prototype that all out and test it. But I'm pretty sure this design here is going to be superior over the current design of just having the one support up there with the radial bearing down here. This is going to give us so much support and so much more predictability. And yes, it's going to take more time, more money. It's going to cost more to kind of create this system and manufacture it. But ultimately, this design right here, I think, is going to last and be, like I said, more predictable, more safe, more trustworthy than just having one support above where the shaft's being loaded. Okay, I got cranking on this design, and there's one thing for sure. This is definitely the point where you start having to think about DFM, which is design for manufacturing, and ensuring that you know how your part is going to be manufactured, like what method it's going to be made, and also making sure your part is still doing the functions you want it to do. So if you're just 3D printing this stuff, like I'm doing right now, and you need some random little bolt somewhere, you just stick it there in the model and you 3D print it. But if you want to machine this thing or make it out of sheet metal, it doesn't work that way. You got to consider a lot of other factors into how the parts are actually manufactured. So that's what design for manufacturing really means, is when you bridge that gap between you have your prototype or your concept and then how it's actually going to get made through a certain or specific manufacturing method. So let's go over these prototypes that I've been working on and sort of explain the progress that I've made there. I'm really stoked. I got this thing like absolutely dialed right now, so check it out. Okay, here was the first flange we made, and then we went over adding the second sort of area for there to be 2 of these bushings instead of 1. So we added that here, an upper and a lower. I happened to run out of filament halfway through this print. That's why it looks like that. Over here, I was playing around with some different sort of like mounting methods for attaching it to the shifter. Right here, you can see I was working on dialing in some more spacing here between the 2 bushings. Once I got that figured out, then I was kind of working on these shafts. This is the shaft that's going to go in the middle, sort of hold the bearing and float, right in between these bushings here. So I worked on those a little bit, and then this is like a little control lever. This is kind of the last main component to this design, is a way to control actually the positioning of this sort of lockout onto the shifter. So this right here connects to the shifter and then connects to the lockout, and it controls it. Here's some different springs. I just went down to my hardware store and got a handful of springs that I thought, hey, these might, work. These might kind of like fit in here just enough for me to test and see how everything works. This spring, I think, is actually out of my original STI reverse lockout lever. When I first started designing shifters, I have all the parts still, and yeah, this spring I think is actually out of that, and I used it and I really liked it when I was testing it out. So before I show you the 3D printed part, here is the actual assembly of the totally like dialed in, ready almost to manufacture kind of, let's call this the upper assembly to the lockout. This is kind of like our main body here. Let me try and highlight that here. So this part, this is like this part. This is housing and connecting everything, all the components to the actual shifter. So we've got that. We've got a little bracket on the side here that it's going to be like kind of a clamp. So that's where it's going to clamp on. And then over here, we've actually got our bearing. And then we've got a little screw going through here. We've got our lever up here going into our collar for the reverse lockout control, and also just the control of the whole lockout system. And then down here we've got our spring and a little retainer. I played around with some different ideas with where to put the spring. I tried putting it in here, and it was just, there wasn't enough space. It was way too small, and then we would have had to make this part way larger and kind of change a lot of things about how the design loads and everything. And it was just smarter and better to just increase the length of this shaft down here and place the spring here. And that was the best place I found to put the spring. I tried kind of playing around with having it up here, in here, and ultimately I decided, well, let's just put it down here and lengthen that shaft out the bottom a little bit. We got the bearing here. This bearing that we're actually going to be using is the largest bearing. This is the one I'm going to start with testing first. It is the biggest one of all the ones we ordered, and it's just going to give us like a lot of room to work with having this larger bearing. So this part, here you go. This is the fully like mocked up 3D printed model right here. So here's our spring on the bottom. We've got all of our retaining rings holding the bearing. You could call it radial, or sorry, not radially, axially fixing the bearing here to the shaft. That means this bearing, it's not just pressed onto the shaft. We have to actually secure it. We don't ever want that thing to move. So we've got little retaining rings in there on the bottom and the top that limit motion and fix that axially onto the shaft. We've also got a retaining ring down here and this little component here that holds the bottom of our compression spring and then actually loads it against that retaining ring. And up at the top here, we've got our lever, of course, that connects to the rest of our shifter. And then right here, we've got a little hinge point. I've got a little screw that passes through the lever and the shafting. And this is actually more of a hinge right there. So check that out. Okay, now I want to show you actually like what goes into prototyping out and like drawing up and creating the files and the drawings and all the information to really manufacture something to spec. So for example, I'm going to show you this shaft right here. Okay, this is the actual drawing that I created and submitted to a shop to have this made on a lathe for the prototype. Something that really came into play here is with how like tight the tolerances are for the retaining rings, kind of compounded with the fact that we have so many compounding tolerances. We've got all these retaining rings that have to be placed from a certain datum, from a certain specific area that if they're placed in the wrong spot, then the system won't work exactly how I want it to work. So that really came into play here, and pretty much what that means is that we have a retaining ring here, we have one here, we have one here, and we have kind of like a stack up of tolerances. So this groove here for the retaining ring, it has its own tolerance for the groove. And then there's a tool that has to actually groove that, and then it has to come in and groove this. Well, these could be different sizes. The actual retaining ring itself could be a different size in here. And then you have to apply a tolerance. You have to tell the machinist, hey, it has to be within this certain tolerance that's acceptable, or this isn't acceptable. So you have to add all those numbers up, and you have to make sure at the low limit and the maximum limit of all your tolerances that your part is still going to be able to work correctly. That can take some time. Reviewing all of the retaining ring tolerances themselves, reviewing the tolerances that I've applied to this, and then trying to just, like I said, correctly placing all the tolerances and creating all the nominal positions for everything. And then the last thing I want to show you on this design is actually sort of a similar concept with the screw. This right here, this screw has a shoulder. It's really just called a shoulder bolt, and it passes through this lever. It passes through the center of this shaft in here and connects the two parts right here with the shoulder bolt through this hole. Now, it's very important that this hole is not too small and that this hole is not too big. If it's too big, what'll happen is the whole thing will drop down too far because now the bolt's at one end. If it's too small, well, this thing isn't going to move. When you go to pull up on it, it's just going to be locked onto it, more of like a press fit, kind of like how the bearing is on here, and that's not going to work either. So really, here's the little shoulder bolt right here, and I'm going to show you like how to do this. And this is literally the thing you have to do on everything to correctly tolerance your drawings and your parts. So right here, this is the size, the nominal size I want. I want this hole to be 4 millimeters in diameter because I've got a 4 millimeter shoulder bolt. Now I know that a 4 millimeter shoulder bolt isn't actually 4 millimeters. It's made for a 4 millimeter hole. Right here, this is the tolerance that I've come up with for this hole. I'm telling the machinist this needs to be a 4 millimeter hole. It cannot be anything less than 4 millimeters. It cannot be anything more than 4 plus this number right here, 0.100 millimeters. Okay, if it's too big, like I said, it's going to float down. If it's too small, if it's undersized, anything under 4, then it could bind up, and this won't be a nice, smooth, sort of like hinge pivot point anymore. Now I busted out my micrometers to show you actually that this, when it's ordered, it's 4 millimeters, but it's not actually 4 millimeters. There you have it. This bolt is actually 3.967 millimeters. And that is very intentional that it's undersized from 4 millimeters for all of the purposes I just stated. And it's really just barely smaller, but if everything's machined correctly to those tolerances, this will work exactly how we want it to work. Here's the assembly actually attached to the DM1 shifter. There's still a thing I need to do to this to properly locate it onto the shifter, because right now we have a round surface connecting to another round surface. So that means we could technically mount this thing anywhere we want. And when this thing is sent out to other people and tested, it needs to locate into a very specific place because of how everything's going to be moving. It can't just be mounted over here or over there. It has to be in one spot. So I'm going to use the side, this nice flat edge of the shifter here, and I'm going to put some sort of screws or some sort of flat locating surface inside of this housing here to locate onto that nice flat surface, so that way when you install it, it can't rotate. It can only clamp down, and it's going to be perfectly perpendicular to the side of this shifter here, because we have that nice flat edge to locate onto going all the way up the shifter. So I'm going to go ahead and add that, and I've got to make the guide that's going to be over here for the actual bearing, but I'm really happy with how this has turned out so far. I've got this shaft being manufactured, being prototyped right now, and this stuff isn't going to work to be 3D printed anymore. And because of that, I have some huge news for you guys. The shop, I don't know if you've looked in the background at all, but it did not look like this at all when we first started filming. Probably even the beginning of this video, it looked a little bit different. So there was really only one choice I had. I've got to make this out of metal.